Hi class, so this section is 14.7. This is strong and weak acids and bases. So if we look at hydrochloric acid and hydrofluoric acid, they're both in the halogen column with the chloride and the fluoride, but one is a strong acid and the other is a weak acid. Actually, hydrofluoric acid is the only weak acid in the out of the halogens. So hydrochloric acid is strong. That means it completely ionizes. That's a fancy word for completely separates into ions in solution. There is no hydrochloric acid left. It is strictly hydronium ions and chloride ions. However, with hydrofluoric acid, it is a weak acid. And because of that, it does not want to separate into ions. It wants to stay intact, and it works really hard to stay intact. So there will be very few ions in solution, and when there is enough ions in solution, they will actually start a reverse reaction to put themselves back together, back to hydrofluoric acid. They want to stay as HF and not as hydronium ions and fluoride ions in solution. And the strength of an acid is based on the amount of hydronium ions produced in aqueous solution. So strong acids, the 6 that we consider strong, completely ionize. They completely separate. Anything that's not those 6 are considered weak acids, and all the weak acids are different strengths within themselves. Some are stronger weak acids, some are weaker weak acids. But it's all based on the content of hydronium ions produced in aqueous solution. So a strong acid dissolves in water, completely ionizes into hydronium ions and chloride ions. I've already said that, but there is no intact HCl. So how do we know which one you're dealing with? Well, in this case, this very clearly shows one forward reaction happening, and there's not another reverse reaction here. There's not an arrow going in the opposite direction. This means there is no going back. It's one way only, and it will always stay in, it'll stay in the hydronium ions and chloride ions, because the attraction to the water is stronger than the attraction to each other, meaning the hydrogen and the chloride. They will split apart because the water will hold them apart, and there's not enough attraction between them to come back together. Strong acids, so pretty much here is a little bar to give you an idea of what we're talking about. This is hydroiodic acid, and it's a strong acid. Again, dissociates into 100 ions 100%. There is a large concentration of hydronium ions and a large concentration of the ion that's attached to the hydrogen. So in this case, you see there's a certain amount of hydroiodic acid. Talk too fast. And as you can see, you see the graphs, they equal. So that means that there is no hydroiodic acid left. It is all hydronium ions and iodine ions in water in solution, in aqueous solution here. So let's take a look at water before we start looking at weak acids. Pure water, meaning H2O, is a molecule. It's not a good conductor of electricity, because if it's pure water, it should have no impurities whatsoever in it. It's strictly molecules of water. Now, the danger of using electrical devices comes in when you start dealing with impurities in the water. So when you take a shower, all that buildup, that calcium buildup, those are the ions that are allowing all that buildup and grime and everything that you see. Pure water doesn't have that. But when you do have those impurities or those ionic compounds, that will allow an electrical charge to carry through the aqueous solution. Even a small amount will allow that to happen. So you've got to make sure you distinguish between pure water and water that has ions in it. Ions will carry an electrical current. Pure water will not. And why am I bringing this up? Because pure water will not conduct electricity. Here's a nice visual. This is a light bulb. We actually have this at Citrus, this little get up, and I've done it for my classes many times. You guys don't get to do this, but I do it as a demonstration, or your instructor would have done it. And we stick these probes into different solutions, so you can see the light bulb, and if it glows, and if it does, how bright it glows. It's actually really neat to put this concept and see it in person, but unfortunately not now. But we got some fantastic pictures. So pure water does not conduct electricity, as you can see. Pure straight H2O, nothing happening here. There's no impurities, no ions in it. And I say impurities because when we want to work with reactions in a lab, I don't know if I mentioned, I probably have. I've worked in a lab I still am employed by a lab. When we want water, we don't want tap water. We don't touch tap water. We use very, very filtered, removed everything, a very high process, expensive to get water to with our reactions, because we don't want anything to interrupt what our goal is for that, what products. So strong electrolyte solutions, so ions in, so here we have HCl. Because this dissociates into ions, this will carry a current, and it's a very bright current. You can see this bulb is very, very bright. So there's a big difference between pure water and water that has ions in it. So 6 substances that are considered strong acids. Here's the list of them. We have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Notice this is diprotic. I'll talk about that in a minute. These are the 6 strong acids. That means that only these 6 are considered strong. They completely dissociate into ions in aqueous solution. If you are asked about an acid that is not one of these 6, it's a weak acid. Now, what the different, if we were in person, you would be expected to memorize these. It is in your best interest to understand these and feel comfortable with them, because when you get to Chem 111, this stuff's going to come back. Now, strong acids has nothing to do with concentration. Concentration, you can make a very, very strong concentration of a weak acid, and it still will only disassociate a certain amount. So concentration, the molarity of a solution, is not the same thing as considering a strong and weak acid. This is the properties that go with these acids. It has nothing to do with concentration. You don't see any concentration of any molarity on these. These will just disassociate. Okay, so we have 5 that are monoprotic. This is a fancy word for saying it's one hydrogen ion or proton that will leave this. And if you see, these are halogen, halogen, halogen. This is halogen with an oxide with it. Okay, so monoprotic means one ionizable proton, which is right here. Diprotic, a sulfuric acid is an example of a diprotic acid that contains 2 ionizable protons. So here it is. Now, the funny thing about this is that it only loses 1 at a time. It's not going to lose both at once. And once it loses 1, it's done. It is now considered a weak acid. So we're going to see it on another chart, minus one proton. As it states right here, sulfuric acid, H2SO4. This is a strong acid. When the proton leaves, what's left over is now weak acid, because there's still 1 more hydrogen that can go. And that one's harder to come off than this first one. So a weak acid, when hydrofluoric acid dissolves in water, only a fraction of the dissolved molecules ionize. That's because it has a stronger attraction to itself than it does to the water. So very few ions will come off here. And as more come off, they will start coming back together, because they will start colliding with each other, and then it will start a reverse reaction. And then it'll be in equilibrium eventually, where one will come off, and one will separate, one compound, one hydrofluoric acid molecule will produce hydronium ions and fluoride ions, but they will come back together and one will go back. So it's 1 and 1, and it'll start doing this equilibrium until something disrupts that system. It'll keep going forever. But if you even look at some of these pictures here, you can see that there's 1 hydronium ion and a fluoride ion, and the rest is intact. And that's pretty much weak acids. They don't want to give up. They don't want to separate. They want to stay together. And when you do separate them, they're going to come back together and push back the other way. That's what a weak acid is compared to, let's go back. HCl, they want to separate. They don't want to get back together. They're done. And here, if we look at weak acids, so here's another bar graph. And again, they don't disassociate very much. So as you see in the purple, there's way more purple than there is hydronium ions or fluoride ions. So you can say for this many amount of molecules, there's only 1 hydronium ion produced and 1 fluoride ion produced. For instance, I think acetic acid is a weak acid in aqueous, which makes vinegar. And I think only 1% of the ions comes off. That's it. That's what makes that so sour, is just 1% of that. So if we look here, we can see that we have hydrofluoric acid, and once it starts to ionize, it mostly doesn't. It stays. Only a very little bit has been reduced to hydronium ions and fluoride ions. It is mostly hydrofluoric acid. It's gonna stay that way. It does not. It's not going to ever look like a strong acid. So this is a weak acid. How can you tell a weak acid? Because these fancy little arrows right here will tell you you're dealing with a weak acid, compared to, let's go all the way back to a 1 arrow. That's, if you have a balanced equation, that's going to tell you, if you have to look at it, are you dealing with a strong acid or are you dealing with a weak acid? Your best interest is to memorize these 6 because it makes life easier. 6 is not a bad deal. And if it's not one of those 6, it's a weak acid. So here's a comparison of the two. I should have just went to this slide. Forgot about it. You can see this completely ionizes, and you can see equal amounts. You can see, if you can count them, you can see they're all matched up, which would have been pairs, but now they're separate. And here, it's mostly intact. So this is a difference between a strong acid and a weak acid. Weak acid also has these fancy arrows that go in opposite directions. And a weak acid is a weak electrolyte. So it's got a very, very dim, because it doesn't have enough ions to carry a very hot, to create this bulb to be really brightly lit. So it's going to be very weak, but because there is ions in the aqueous solution, it will carry a current. Okay, so here is some examples of weak acids here. So most carboxylic acids are weak acids. We have 2 of the weak acids shown here are diprotic and triprotic. Sulfurous acid and carbonic acid, this is what you're seeing right here is carbonic acid, are weak in both of their ionizable protons. And phosphoric acid is weak in all 3 of them. So what's it saying is that this carbonic acid, even though it has 2 hydrogens, both of them are weak acids. This can lose a proton, lose a proton, lose a proton. All of them are weak acids. They're not going to be strong. Now here we go. This is the one I was talking about. Here we have sulfurous acid. Sulfurous acid is a weak acid. So we have sulfates. Actually, I wasn't talking about this one. This is the less oxygens. We have sulfate, which is SO4, and then we have sulfite, which is SO3. This is sulfurous acid. So even though it's got 2 hydrogens, it's sulfurous acid, which is from the sulfite. It is a weak acid. And sulfuric acid, this is what I was talking about, is diprotic, but only the first proton is considered strong. After that, the second one is weak. And here's my example. So here is the first one. It loses the first hydrogen, and now we have bisulfate or hydrogen sulfate, however you want to call this. And this now is a weak acid. So in order to lose that one, it's going to have an equilibrium arrows. So when you're dealing with weak acids, you have equilibrium arrows. When you're dealing with strong acids, you have a forward only arrow. So once this is done in the forward, not going back, now you have this compound. If it loses that other proton, it's doing it with forward and reverse arrows, which are equilibrium arrows, because this is a weak acid. As much as what comes off is going to go back on. Okay, so let's determine the concentration of some acidic solutions. This is not a difficult thing. You're probably thinking, well, how do I do this? There's no calculations. You don't have to know calculations to know this. This is knowing the 6 acids, and if it's not one of those 6 acids, it's a weak acid. Okay, so first thing you should ask, are you looking at a strong acid or a weak acid? And I'm just going to show you the answers because it's easier for me to explain. Extra slide. Okay, since HCl is a strong acid, it completely ionizes. Remember those bars that are equal? So that means that the concentration of hydronium ions is 1.5 molar. And these brackets mean concentration. So anything written in there means that you're looking at for the molar concentration of whatever that is. So the molar concentration of hydronium ions is 1.5 molar, which matches the molar concentration of hydrochloric acid. Okay, so now we have acetic acid. Acetic acid partially ionizes. The calculation, we don't know what the calculation is, and it's funny, it tells you right here that you're not going to know this because it's beyond what you have to know. But the main point of this is, remember that fancy bar graph that I gave you guys? The concentration of the hydronium ions is never going to match the concentration of whatever this is, because there's not enough. It's not enough to give you a molarity that's going to match that. So it's going to be less. So if this is a 3 molar of acetic acid, the concentration that's in ions is very small. So it's going to be less. And that's all you need to know. It's going to be less than what the concentration is for the intact acetic acid. And nitric acid is a strong acid. So it is 2.5 molar, because that's the amount of because it separates completely. Hydronium ions are going to match that concentration. Now let's take a look at strong acids and strong bases. There are also 6 strong bases that make up a the strong base. Repeating myself here. Strong bases are also strong electrolytes. They are formed from metals of group 1 and group 2. They also completely dissociate in water. So here's an example. You have potassium hydroxide in solid, but once it's in water, it will dissociate as a base. And the amount of hydroxide ions is how you can determine how strong of a base it is. So these all completely separate, and because they completely separate, you have a lot of hydroxide concentration. The difference here, unlike diprotic acids, which you will lose 1 proton at a time, for bases, you're going to lose both hydroxides immediately. So if this was any one of these, well, based on solubility too, so let's take that sodium hydroxide, let's pick one of these. You would have 2 hydroxides to, if there was a fancy, I'm messing this up. Basically, I'm not even going to give you an example because I'm going to confuse you and I'm going to confuse me. Just know that with strong acids, you lose a proton at a time, and with hydroxides, strong bases, you're going to lose both of them at a time. They're both going to be gone. It's going to completely separate. It's not going to try to stay intact. Whereas with a strong acid, it still tries to hold on to that other proton. Okay, so sodium hydroxide contains no intact sodium hydroxide. You can see here it is completely all in as ions in solution. Now, weak bases. Weak bases are very similar to weak acids. They want to stay intact. It doesn't want to. It doesn't want to be in hydroxide form. It wants to go back to what the reactants are. So they are poor acceptors of protons. So when they do, when, for instance, the water does dissociate, it will, when there's enough ions here, they will start in the reverse direction and bring back the reactants. And this will be equilibrium. So for every one that dissociates, one will come together and come back. They produce very few ions in solution. Same thing, think of a hierarchy of weak bases. Some are stronger weak bases than others, but there's equilibrium arrows. They want to stay it wants to stay intact with the water, and the base wants to be on its own. So when ammonia dissolves in water, it partially ionizes to form ammonia and hydroxide. So even though ammonia doesn't have hydroxide on it, it produces hydroxide ions from the reaction with water. So this is where the Bronsted-Lowry base definition comes in, because it can accept a hydrogen. But remember, with Arrhenius acid definition, it would have to produce hydroxide ions. It does, but not directly from itself. So here we have, when ammonia dissolves in water, it partially ionizes. So it takes the proton from the water and forms ammonium ions and hydroxide ions. But there's only a small fraction that do this. And then enough of these are in solution that they will start in the reverse reaction. So this is a weak base. This will have equilibrium arrows. And you can see it right here. So once it comes off, it's going to go back in. So weak bases all have equilibrium arrows. Weak acids all have equilibrium arrows. Strong bases, strong acids, forward reaction arrows only. All right, so let's determine the concentration of hydroxide in each of these solutions. So you should also know the 6 strong bases. It makes your life easier when you're dealing with exams and so forth, trust me. And if it's not that, then it's going to be considered a weak base. So here we have potassium hydroxide, which is a strong base. So the concentration of hydroxide ions is matching the molarity of the intact. So it's going to be 2.25 molar. Okay, so now let's look at methylamine. Methylamine is a weak acid because it's not part of the strong acids. So instantly, whatever the molarity is not going to match the hydroxide ion concentration is not going to match the intact molarity. So that's all we need to know, is it's going to be less. And now we have strontium hydroxide. Strontium hydroxide is a strong base. It's going to completely dissociate into 2 hydroxides and strontium. So the 2 hydroxides compensate for the 2+ charge. There, I said I got it right this time. Strontium hydroxide, though, forms 2 moles of hydroxide. So it's not going to match this concentration because you have to consider that there's 2 moles of ions in it. So you're going to have to multiply that molar concentration, and that's going to be 0.050 molar to account for the 2 moles of hydroxide concentrate that are in ions, not 1.